Everyone. Hello, Will.
Hello.
I'm Daniel Rodanegren. I'm the North America Quantum Science and Engineering Lead here at Qblox, the sponsor of today's conversation. This is the very first talk of our webinar series, and I honestly couldn't imagine a better kickoff to get started with a better speaker. So it's my pleasure to introduce Professor William D. Oliver, uh, one of the true pioneers in quantum computing. Will has worn many hats across academia, government, and industry, and his impact on the field is enormous. So at MIT, he directs the Center for Quantum Engineering and holds a joint appointment in the Physics and Electrical Engineering Department. He also has shaped the field nationally through his role at the White House National Quantum Initiative Advisory Committee, and he co-founded Quantum Atlantic, translating MIT breakthroughs into industry. On a more personal note, I've had the privilege of working closely with Will, first as a collaborator, then as my postdoc advisor, and always as a mentor. So I've seen firsthand not only his scientific rigor and engineering discipline, but also his commitment to training the next generation. So it's a real honor to share the stage with him today. Very exciting for our conversation. And as we go along, I invite everyone watching on YouTube to post your questions in the chat, and I will select a few at the end to bring them into the discussion. So without further ado, let's dive in.
Sounds good. Yeah, thank you, Danny. Thank you for the very kind introduction. It's my pleasure to be here.
Thank you, Will. So let's see, we'll be touching on the state of quantum hardware and scaling challenges, the role of the quantum ecosystem and the workforce, and a bit on the future of quantum classical integration. So, Will, to start off, having worked across academia, government, and industry, you really bring a unique perspective here. From where you stand, where do you see as the most important engineering milestone in the quantum hardware over the last few years, and which challenges kind of feel essentially solved, and which still remain fundamentally hard, so to say?
Yeah, and Danny, let me just make sure I understand the question fully too. Are you thinking just about superconducting qubits, or do you want to speak more broadly than that?
I will leave that up to you, Will.
Okay, well, why don't we start with superconducting qubits, and then we can talk about others as well.
Excellent.
Yeah, 20 plus years ago, when I got started in the field here with Terry Orlando at MIT, superconducting qubits were kind of dogs, right? If you read Nielsen and Chuang, Ike Chuang and Michael Nielsen's textbook on quantum, they wrote it more than 20 years ago, and in that textbook, it would talk about cavity QED, they'd talk about trapped ions, and they would talk about the modalities then, and it was kind of everything else chapter, right, or section of that chapter, and superconducting qubits were in that everything else. Because at the time, their coherence times were low, and they weren't as performant, certainly not even close to the trapped ions. And so then, you might wonder why I got in this field, but I found it to be truly interesting, and I thought, well, let's give it a try. And to get to your point, from a hardware perspective, from say around 2003 to 2013, there was a lot of work in superconducting qubits just to get them to work, and to work well. And by 2011, 12, we had some results in collaboration with NEC, Yasu's group in Japan, Yasu Nakamura, where we had a qubit that had 10, 20 microseconds coherence. And Yale, of course, had the 3D transmon at that time, which that's Hani Paik and Rob Sholkoff's result, and collaborators. And that really taught us that surfaces are important, right? The surfaces of these qubits is really critical. And shortly thereafter, Chad Rigetti and IBM also had a 3D transmon result. And of course, Chad went out and formed Rigetti. So at that point, qubits were close, somewhere in the tens to around 100 microseconds coherence times. But that's, of course, just the beginning. You think about David DiVincenzo's criteria, you need 1 and 2 qubit gates. Okay, great. But if you want to build a quantum computer, you need a lot more than that. And so then the question from 2013 maybe until today has been about how are we going to scale up, right? And so it involved a few things. One being 3D integration is critical, and work that we've done here at MIT and Lincoln Laboratory in particular, where I spent about 20 years of my career, to advance 3D integration. That's been very important. And in addition to that, the fabrication engineering that it's been pushed forward by many of the companies, I would say IBM and Google and now AWS, and of course the universities as well, has been quite important. And even exploring new materials and fab techniques. And coming to mind is Natalie De Leon at Princeton, in collaboration with others there, have pushed forward the field. And so this is all great from the hardware standpoint. But then of course you realize, okay, I've got a few tens to 100 qubits and I need to control them, right? And the question is, how do I control large numbers of qubits? And as an academic researcher, I'm sure others know this, that you have these large-ish beige boxes, and they would control 1 qubit. And we started advocating, and I know others as well, from the teens, that what you really need is a chassis-based environment where you have cards that go in, arbitrary waveform generators, microwave controllers. Ideally, it should be digitally synthesized, direct digital synthesis, or DDS. We want to have FPGAs embedded, right, so that we can really control what's going on, have feedback, act on that feedback, have the feedback distributed across the chassis planes, and also chassis to chassis. So that's been a very important advent, I would say, within the last 10 years, is the move from the large beige boxes to the chassis-based environment for the control electronics that we need to control not just superconducting qubits, but also semiconducting qubits, and even some flavors of trapped ions, like Oxford Ionics, for example, which was recently acquired by IonQ. So that's also been quite important. And then maybe the last thing I'll say, so I don't drone on forever, is that what we're trying to do today, and we saw a great example of this in the Willow demonstration by Google last fall, is quantum error correction. Because if we want to realize the full promise of quantum computing, we're going to need to process information for much longer periods of time than the intrinsic coherence time of our qubit. We're going to need much higher fidelities. The error rates have to go down. You could ask, maybe we can get into this, but the short statement is, we've worked very hard, you worked very hard with us here, Danny, to get error rates down to 1 part in 1,000 or 1 in 10,000. I think the best we've achieved in our group here at MIT is 1 in 100,000 for a single qubit fidelity. But if you want to do something at scale and achieve not just quantum advantage, but quantum economic advantage, and by that term, what I mean is, and this was coined by Jonathan Ruane, I co-teach a class in Sloan with him, Sloan School of Management, quantum economic advantage, right? Which is, when is a quantum computer going to do something for me that's commercially relevant? If we want to do that, those types of algorithms are going to require 1 billion or 1 trillion operations, which means the error rates need to be at that level, 1 in 1 billion or 1 in 1 trillion. And that's what, 6, 7 orders of magnitude, something like that. We're going to work really hard to make our physical qubits better, but I don't think we're going to make it all up. But what we can do is do quantum error correction. And what Google showed last fall is that going from a distance 3 to a distance 5 to a distance 7 code, each step, they increased the number of qubits, and each time they did that, the error rate went down. And that's fantastic, because that means I added more qubits, but the performance of the system got better. And that's what we need to do if we're going to realize the promise of quantum computing.
That's great. Actually, let me build on that, Will. And maybe as we move, let's say, beyond fundamental research, what do you think actually are going to be the biggest challenges you observe in translating these quantum innovations from academic labs into robust, reliable systems needing to industry? You mentioned quantum error corrections. Is that the main one you would think of? Well,
certainly quantum error correction is a key enabling demonstration that we have to do, and it's not a step function. Oh, I did it, it's done, here we go. We often use the analogy, or at least I often use the analogy of the Wright Flyer. And we think back in time, you see the Wright brothers, and one of them's flying the plane, and that was the dawn of commercial aviation. But that wasn't the end of it, right? Nobody goes on vacation getting on that plane. I wouldn't get on that plane. Didn't fly very far. Didn't fly very high either. But the point is that it was not the first time that humankind had flown, actually, right? There were hot air balloons, there were aerodromes, there were airplanes that flew under their own power, but nobody was on board, right? So the point is that Wright brothers demonstration is when it all came together, and it was enabled by some advances in control, actually classical control of the flight of the wings. So then it all came together, and we look at that in hindsight, we say, okay, yeah, that demonstration, still we're 10, 20, 30 years away from commercial aviation, but that demonstration, I look at it and I say, I can see that it's going to come. And I think that what we're seeing today in the field are those types of demonstrations. And a quintessential example is Google's demonstration from last fall. Like, we look at that and we say, yeah, we knew from the 90s and Peter Shor and Andrew Steen and Calderbank that, sure, we know that error correcting codes should work in this way, that as we make the distance of the code larger, the error rate will go down. Sure, theoretically true. And we knew that. But showing it in real hardware, getting back to your question, showing that it actually works, for me as an experimentalist, super exciting, right? You see that, you're like, yes. And I look at that and I say, yeah, no, of course, it's not good enough. The error rates aren't yet 1 in a billion or 1 in a trillion for that surface code. But I can see that it's going to come, and I can believe it. And by the way, in that same paper, they did get to about 1 in a billion or maybe a little better on a classical repetition code, which I also think, okay, that's not what you need for quantum computing, but it's one axis in the sense of what you need for quantum computing. So I found that to be tremendously exciting. So there are these types of milestones that we look for. But your question was about translating research, right, from an academic environment into industry, and that is very tricky. It's also something that I've spent a lot of my career working on at Lincoln Laboratory, where that laboratory at Lincoln does act as a bridge between academia on one side, industry on the other. We're trying to do the best work we can in the interest of the government. But it's fraught, it's tough. And it's tough because there's this valley of death, as they call it, during this translation where, what universities are very good at is trying a lot of things very quickly, failing fast, and publishing papers based on that. And that's important because, if you're at the early stages of a research endeavor, a field, you don't really know what to do. Right? And you need to try all sorts of things to know, okay, what's the right material and what's the right way to make this thing work? Does my concept even work at all?
I've been there, Will.
Yeah, you've been there. You've been there. And, so that's very, very important. But the motivation there is not to make something robust, reproducible, extensible, commercial. Not yet, right? And so we're not thinking of polishing, what is the cleanest, best fab process that I can do when I don't know what to do at all, right? Rather, you're going to try a lot of different things and see what works. That's what academia is good at. And then, I'm both an engineer and a physicist. I was trained as an engineer, so my ethos is a little bit more oriented towards, okay, let's make it reproducible, let's make it extensible. But it's still a different story from what people do in industry. If you look at what companies like, say, Intel, to use an example, can do, or TSMC, or Samsung, they make chips with billions and billions of transistors, right? And to get to that point, of course, people in academia seeded many of the ideas, but the actual process development that was used to make that robust, reproducible processor, a lot of that has to be done in industry because first off, it's very expensive to do that. And also, it's not the kind of thing that lends itself necessarily to publication or to good training of students. So academia, of course, has a role, both in exploring the space, kind of identifying good candidates, seeding those ideas, and importantly, training the workforce. And then industry is great at taking those ideas and, you know, making them commercial. And it's no fooling, it's got to work. It's got to work every time, or people are going to get frustrated and they won't buy it. And then the question is, how do you bridge in between? And that's what's tough, and that's why there's a valley of death. Yeah.
Thank you. So, you know, maybe looking back at your own journey in the field and over the last decade, what has been the most important shift, you would say, in your thinking about building scale quantum hardware? So as we've moved from, first demos to scalable platforms, what assumptions about control systems, modularity, or software integrations did you have to rethink?
Well, I think part of this, because I spent a lot of my career at Lincoln, I think we were a bit ahead of the curve in thinking about how to scale, what do we need, because Lincoln is effectively a national lab. Our job is not to just do what academia is doing, right? And so we shouldn't just repeat what they do. At the same time, we have more flexibility in industry because we're funded through the U.S. government. And I should mention that I keep saying we. I'm talking about the period of time that I was there. I stepped down in 2003 because we started Atlantic Quantum. But I'm talking about during the time I was there, from 2003 to 2023.
That's
and
20 years.
That work continues today, of course. That we were a little bit ahead of the curve, I would say. And so we were thinking about process modules, so fabrication process modules and material science and a lot of materials analysis, even going back to 2008, 2009, 2010. So we were thinking about a lot of those things, and of course that's been picked up on by many groups. It's not, it's not rocket science. It's just we were a little bit ahead of the curve, right? And so we thought a lot about that. I would say 3D integration was one of the main thrusts that we had from 2012-ish to 2020, really thinking about how are we going to get all these wires, all the connectivity we need into a processor. And it involves thinking about room temperature down to cryogenic temperatures, and then at the cryogenic temperatures, getting those signals to the qubits. And the reason it's important, and I think the reason a lot of people weren't thinking about it at that time, was that, okay, makes sense. I'm trying to make 1 and 2 qubits behave better, maybe 5, maybe 10, and those you can bring wires in from the side. So why complicate life by trying to build this complicated 3D structure when I'm just trying to test a few qubits? So what we said was, okay, yeah, that's great. A lot of people are focused on that problem. We're going to focus on the future because we believe it's going to get there to the point where we need to bring in connectivity to a large number of qubits. And even at, say, 16 or 25 qubits, you realize it gets pretty crowded trying to bring everything in from the edges. So what you need to do, of course, is bring the wires in from the 3rd dimension. And that's what leads to 3D integration. So, that we were working on, as I said, in the teens. We also had folks at Lincoln who were working on the software stack, right? And that was both from the perspective of how do I simulate the behavior of a quantum computer and the abstractions I need to do that, because clearly we can't simulate exactly the time dynamics of the Schrodinger equation perfectly for very large numbers of qubits. If we could simulate a quantum computer on a classical computer, we wouldn't need to build a quantum computer. We would just simulate it. So of course there's brute force simulation, but then you want to simulate a larger system, so you have to abstract in a smart way. What does that abstraction look like for quantum computing? So I had folks thinking about that. And what I found interesting about that is it works in both directions in the following way, that you start with an algorithm, somebody typing their fingers on a keyboard, inputting that algorithm you have a logical controller which is interpreting, you know, what that algorithm is, compiling it into the gates, sending that down to the physical hardware. You can simulate that whole stack. In fact, you want to simulate that whole stack. But in building the simulator, if you think of it in reverse, or from the other perspective, I should say, that's actually the control system of a real quantum computer, right? You actually have all these pieces, and in one direction you're simulating, but in the other direction you're executing. Yeah. So I think that is certainly standing up. Many companies, of course, today are, you know, doing this in spades. I'm thinking IBM and Google and AWS and Microsoft, and, you know, I'm sure that I'm forgetting many, and I apologize for that. But we know these names, right? And we know that they're working on this software stack. And then I think the other thing that's really changed since, say, 2020, I think, you know, John Preskill had coined the term noisy intermediate scale quantum, or NISQ. I believe it was around 2012. And it was a good idea. It was a very good idea, which is, look, what can we do with the quantum computers we have today before we have quantum error correction? What can we do that's useful? And people have been thinking about that for a long time. And I think one shift around, I don't know if it's exactly 2020 or what, but one shift is that it doesn't look like, I don't want to say it's not going to happen, but it doesn't look like that is a viable path to quantum economic advantage. I think that the community is sort of coalescing around one of two ideas. And one is, look, you just got to do error correction, you got to do it at scale, and then we will have universal fault-tolerant quantum computing. And the other idea is, well, okay, and it's hanging on to the NISQ idea, which is that maybe, for example, with neutral atoms, maybe with superconductors, maybe with trapped ions, we can emulate a quantum system. We can set up a system of qubits, but we're not really operating them as qubits. What we're doing is we're coupling them with strengths that we set specifically, and we set the energy of the qubit specifically, so that they're mimicking a real system that we want to understand. So that, you know, most people would call that simulation. I call it, or prefer to call it, emulation, because I'm using one quantum system to emulate another quantum system. And it goes back to, I think, Richard Feynman's original idea, and Yulee Manin and others in the early 1980s of what a quantum computer would look like, right? It's really an emulator. So I think, you know, barring that, you know, in addition to that, I think the main thrust right now is trying to do quantum error correction, because we know that we're going to need it to attack these problems at scale. Oh, and one more, I forgot, one more, is that we absolutely need people thinking about quantum algorithms and the abstractions we need to generate new quantum algorithms, because we need more quantum algorithms. And that will be helped as the hardware progresses. You know, it is a bootstrapping process where the more people we have with their fingers on keyboards trying out ideas, the more quantum algorithms we will discover. And so that gets a lot more exciting as the hardware becomes more performant. And so I think that we will see this bootstrapping effect. Better hardware, okay, maybe there's some new algorithms. Better hardware, okay, new applications of those algorithms. But we need to do that. We need people thinking about it, because we don't have enough quantum algorithms right now. And we need, you know, I tell companies this too. We have an industry membership group here at MIT in our center. And, you know, what I tell them is, look, have a person or two at your organization who's thinking about the problems you have, because you know your problems the best, right? And then have those people understand or figure out what quantum algorithms we know about today that would be applicable to your problems. Write it down. And then test it on the small scale quantum computers we have today. It probably won't bring you economic advantage yet, but it will bring you something valuable, which is that A, I've got an algorithm that I know is going to solve a problem I care about, and B, it gives me a little bit of insight into the size of the quantum computer I'm going to need in order to get that economic advantage in the future, right? So it's quite informative, and it helps to reduce risk and surprise.
It also seems like a good opportunity to be in the race from day one and be ready for when things are ready to even scale further.
Yeah, well, you know, everybody has to do their own risk-benefit analysis. But I think in this case, people often talk about fast followers versus leaders. Whichever strategy you take, don't be a slow follower, I would say. Because this is a disruptive technology, and you don't want to find yourself one day in 5 or 10 years that your leading competitor is using a quantum computer to do something, and you haven't even thought about it yet, right? That's what you want. You want to make sure that you're ready. It's too early to bet the farm, right? Like we need more performant quantum computers. We need more algorithms. This is a field that is nascent, but growing and maturing. But it's important to be involved and aware. So again, don't bet the farm, don't bet the whole company on this, but also don't ignore it, right? Form a small team. Have people who understand the technology and understand your problems and how the technology will help solve your problems in the future.
Thank you for all that, Will. I mean, I think it's clear we've made really incredible progress in engineering, but there are a lot of exciting discoveries still coming our way.
Oh, absolutely.
So,
yeah.
This maybe naturally kind of brings up the scaling problem, which is at the heart of today's problem, and we've already touched a little bit on it. But when we talk about scaling, let's say superconducting qubits, where do you think is really the most critical bottleneck? Is it in fabrication and material science? Is it in the cryogenic environment, in signal delivery? Is it in the control or the software stack?
Yeah, I mean, I think all of those things that you just mentioned are pieces of a scalable quantum, superconducting quantum system, and they all need to be advanced. I don't know that any one of them is more critical than any other one. It's desirable, of course, that we can, let's start from the beginning, better material science, right? So that we have a better understanding of the surfaces and the interfaces that are causing decoherence. And we find material systems that give us more performant qubits, right? And that very much, getting back to what we said before, that's very much an academic pursuit. Academia can do that very well. But that doesn't mean necessarily that material that you found, that's the absolutely best material, that may not be the one that is commercializable in the future. Because I then have to fabricate that device. And when I fabricate the device, first off, I might change those interfaces, right? But second off, there's this concept of what's called fabrication interaction, which is that I do a step, it's a multi-step process, and I change, say, step 2, and it might impact step 8 in ways that I didn't really foresee, and this is process interaction. And so the optimization of a fab process often involves looking at the materials that are available to you, and you optimize over all of it, right? And so it's in some sense an equilibrium solution, right? Where I might not take the absolute best material, but and maybe I don't take the very, very best way to do step 8, right, in my fab process, but I optimize over the whole process flow from materials to device. And I pick the best way. And what does best mean? It often comes down to yield, performance, robustness, all of this, right? And so it's a systems optimization problem. Yeah. So that still has to happen. And of course, the role of academia is to feed in some of these good ideas. Hey, this might work. Hey, that might work. Hey, I demonstrated this to look really good. But it's really an industry where they're going to say optimize this whole thing to create a product, right? And to create something that really works well. And this is what IBM and Google and many others are doing right now. So that's part of it. With superconducting qubits,
I'm assuming cost will also.
Go ahead.
Sorry, Will.
Yeah.
I'm assuming cost will also get into the equation at that point.
Well, absolutely. Absolutely, the cost comes into the equation because these are hard, thorny problems when you're optimizing across many variables, and you need a lot of engineering. You need to run a lot of wafers. You need expensive equipment, right? It's not about making one device that once worked. It's not even about making 10 or 100 devices. We're pretty proud when we say, hey, I measured this and I confirmed it over 10 devices, right? But if you're going to be really producing, fault-tolerant quantum computers, you need to be fabricating wafers all the time. And it's got to be like water, right? There's no valuable wafer. They're all, just do it over and over and over and over again. And you've got people who are just tweaking and optimizing and optimizing and optimizing. And of course, doing good material science, doing good fabrication engineering. But all of this has to happen. So then the cryogenic environment for superconducting and semiconducting quantum computing, that's also very important. Right now, we operate our superconducting qubits in a dilution refrigerator, which is basically a very powerful refrigerator that can get down to 10 or 20 millikelvin. That's 100 times colder than the background radiation of space, right? People often look at that from the outside and say, well, gee, that sounds kind of esoteric. Can this ever work? And the answer is, of course it can work. If we need a bigger refrigerator, we'll build a bigger refrigerator, or we'll connect two together. But of course, if I didn't have to do that, I wouldn't do it, right? It's not like we elected to do it that way. It's just that we have to do it that way today. And so, trying to raise the temperature, very practical things of our qubits is paramount. And parenthetically, I'll say that people often ask me, which one's going to win, right? Which quantum computing technology is the long-term winner?
Tell us, which one?
Which one? I wish I knew. No, my answer to that is I don't think there's going to be a single winner. I think that technology doesn't evolve that way, right? Technology evolves over time. If you go back to the history of classical electronic computing, we had mechanical machines. Okay, well, I said electronic computing, but initially it was mechanical, and then there were vacuum tube quantum or classical computers. And then that hung around for a good 10 or 20 years. And then there were transistor, but they were bipolar junction transistor-based computers. And then it eventually switched over to something like an emitter coupled logic. And then that became too power hungry. And then it switched over to another type of silicon device, which we now use, CMOS, right? So technology evolves over time, right? And where we used to use CPUs, and we still use them today, but now we're seeing an evolution, since Moore's law, or the Dennard type scaling, really, it stopped around 2006. Our processors have been, 4 gigahertz since then. But we're finding other ways to optimize, right? And that's either 3D integration or, system on a chip, moving to tensor type processing, GPUs, et cetera. So the technology doesn't stay static. Right, and so I believe in quantum computing as well. Superconducting qubits are great today. They might carry us forward for quite a while, who knows? But at some point, someone's going to come along with an innovation or a revolution that changes the game. Now, it might change it in a way that it's still superconducting, but it's a higher temperature. Or it might change it in a way that, nope, it's actually neutral atoms or semiconductors or ions or something else, right? We don't know. I mean, we can keep our finger on the pulse, right? And I would recommend people do that, but we just don't know. So, of course, cryogenics is important, but I don't think it's the showstopper, or I don't think it is a showstopper. What's challenging is how do you get lots of wires and lots of control signals to your quantum processor, right? And today that's basically done in what I would call a brute force manner, or brute force scaling. 1 wire per qubit. And in fact, often 2 or 3 wires per qubit. DC bias and fast flux and my microwave pulse. And keep them separate. Some people try to combine 2 of them together, and now it's only 2 wires. But the point is it's roughly speaking on the order of a wire per qubit. And you can do that at 100 qubits. Sure, you can do it at 1,000 qubits. If you're really a brute, maybe 10,000 qubits. But at some point, this just becomes a losing battle. And the reason is, it reminds me a lot, in fact, of vacuum tube computing in the 40s and 50s. And eventually, the vacuum tubes, they have a failure rate. And they're failing at a rate, if there's enough vacuum tubes, that on average, one's always failing. And so it doesn't run. That's actually how, in part, error correction protocols, classical ones, were first developed, was to try to handle some of this. But it was clear that, another technology would eventually come along that's more robust. So Um, anyways, yeah, so, one wire per qubit is a problem because if I scale that up to 1 million wires, I will have some failure rate, and I need to account for that. I need to be able to either ignore it, accept it, live with it, or find a way that I could fix it, which means warming up that fridge without warming up all the other fridges. Right? I don't want to warm up all 1 million and then cool them all back down again. Right? So there are a lot of these types of systems level issues that people are thinking about, but particularly in industry, I would say, primarily about how are we really going to do this at a scale that's large. Of course, the other way to do it is to try to co-locate the electronics, the control electronics, with the qubits. And there are ideas along this line, cryo CMOS, superconducting electronics, classical superconducting electronics, et cetera. And the startup that came out of our group here, Atlantic Quantum, is focused on exploring some of these ideas. But the goal would be to get to a point where I think you have a few lines coming down to tell the control electronics what to do, and then the control electronics are close enough to the qubits that they then talk to the qubits, and you extract it out this way. We're pretty far from that. I don't think Qblox has a lot to worry about. There's still a lot of work to do, with room temperature electronics for sure, and we'll always need room temperature electronics. It's not like that's going to go away. But at the scale of 1 million, I think we need to get away from 1 wire per qubit. And this is one thing. This is a superpower, really, of neutral atoms. I would say is that neutral atoms can have one laser that's controlling, say, 300 qubits with one laser, one source. Now, how to go beyond that? They need to still figure that out. And but that's the kind of thing that we want to see, is either through multiplexing or some other mechanism, like a crossbar switch or something. With just a few generators, we can control a lot of qubits, right? That's an important problem.
So, Will, since you mentioned, specifically Qblox, let me zoom in on the control side.
Yeah, sure.
For a little bit. And, I wanted to ask you, what do you think is still missing in, today's commercial control stacks? And what kind of innovations, let's say, can unlock the next leap in system scalability?
Well, I think the one major change is what I mentioned before, is we went from the big beige box that held one channel to a chassis-based format where just by sliding in cards that we go to multiple channels. And each card could have, say, 4 or 8 or I don't know, channels. Depends on what it's actually doing. The back plane of that chassis is allowing the cards to talk to each other, so I can take information in, say, from a syndrome measurement, process it, and then tell another card, or maybe even another card in another chassis, what the next pulse should be to do a correction or something like that. So that's important. Direct digital synthesis is quite valuable, and that's challenging because, of course, you need very fast electronics. So it's probably 3.5 or 2.6 materials and chips, but it's becoming possible, more and more to have these kinds of direct digital synthesis where you don't need necessarily the microwave generator. It's just everything's arbitrary waveform. That's quite useful. FPGAs on the cards is useful, and you would say you asked what do we still need to do? I would say making the FPGA programming available and more flexible. And in fact, writing a good interfacial layer where you can program in human language or in some kind of a reasonable programming language to easily access the FPGA and implement on it. That would be quite useful. And, this is happening to various degrees. Don't get me wrong, but making that seamless and bug-free would be useful. The other thing that I would say is that the cost per qubit needs to come down. And that's not just hardware, but it is also the hardware. Meaning that, the cost per channel, and, if it's, even $1,000 per channel is pretty aggressive today. But if you think about it, and you want to build a system of 1 million qubits, and it's $1,000 per channel, that's $1 billion for a quantum computer. And that, you could say, all right, top 500 computer, okay, there's only 500 of those, right? So, the point is that if we really are going to start mass producing these things, the cost per qubit is going to have to come down. And of course, that's driven by the market. So as the market gets larger, then the cost per qubit can come down because you're producing more, so your margins can be less and all that. But right now, the cost per qubit is pretty darn high.
That's a very good point. Thank you for all these insights,
Yep.
Will. So, of course, scaling isn't just about technology, it's also about the people and the institutions kind of building it.
Yes.
So, as the field is growing rapidly, I have the feeling that we have some talent bottleneck here.
Yeah.
So how should universities and industries collaborate to, let's say, train the next generation of quantum engineers? And I don't just mean physicists, also RF, software, system engineers.
Yeah.
That, from what I'm seeing from the industry side, kind of like the ecosystem desperately needs.
Yeah. Yeah, absolutely. Large part of what I've been doing on MIT campus since I came down was oriented towards education and training. And I don't just mean in the group, right? Like we were working together as well. But from about 2017 or 2018, we developed a series of 4 professional development courses at MIT XPro. And each one is 4 weeks long and taken online. It's meant for people who are not quantum physicists, right? Exactly what you're saying is that the rest of the story. And the idea there is that you want people to become quantum aware, but they don't need to be super deep quantum physicists. Of course, you need those people because at some point the quantum mechanics matters. But at some future, and we're still in the transition period, but in some future, if we use an analogy, people who are designing transistor chips don't need to be semiconductor physicists, right? That it's been abstracted to a point where I can still design a circuit with some rules of thumb, engineering. It's not simple, but it's its own discipline. And it's not that I'm going back to electrons and holes and figuring out how they cross on energy bands, right? So this is what we have to do in quantum. So as one first step of many that need to be done, we developed these professional development courses, and we've had thousands and thousands of people take it since then. And in fact, we just introduced a new one, which is about strategy, and it's really meant for executives who really only have about 10 hours or a weekend, not 4 weeks. There are people in this world who just don't have 4 weeks to spend on a course. But so we're still trying to do that. Another thing is, if you think about a quantum industry, as you said, right, it takes everyone. If I speak in terms of a university, we need people from every department contributing, right? Not every person in every department, but we will have people from each department who are contributing, and that means, the chemists who know the important chemistries, what's hard, what's not, biologists, electrical engineers, physicists, of course, and also, the Sloan School of Management, right? If we're going to make a business, we need people who understand business. And so, I mentioned Jonathan earlier. Jonathan Ruane and I have a course, The Global Business of Quantum Computing, that we're teaching in Sloan, and always packed. So we're glad to see it. So we're trying to fill that pipeline. But there's a lot more that needs to be done. And one of the things that we're thinking about now is the abstractions that we need to make an engineering discipline, or quantum engineering. What is quantum engineering? What exactly is that? What are the textbooks that we need? What is the curriculum? Is it mostly just traditional engineering, microwave engineering, let's say, with a little bit of quantum included? Is that quantum what's taught in the physics department, or is it a new type? Not that the quantum mechanics is new, but the way in which it's introduced. Do we go back and do Schrödinger equation, particle in a box, like that? Or do we just start with spin 1/2 system? This is the way it works. Do I need to really learn about the Clebsch-Gordon coefficients? I don't know, right? These are the points. Like, what does that discipline look like? And we need people thinking about that in academia, and we want input from industry as well. because you know, it's also a systems engineering problem. Yeah. And then I guess you had asked about the connection between academia and industry and what we can do. You know, I think internships are an important part of this. They have to be well coordinated. We have to mature the field to a point where, sure, there's IP. Right now it's open, and pretty much anything we do, it's new IP, and so then, you know, everybody's fighting about IP and sign this NDA, sign that NDA. But from an educational standpoint, it's important that we have students who are focused on the right problems, and that can be enhanced by the right kind of experience in industry. But it can't be, you know, the type of experience where it's like, you know, optimize this one thing to the nth degree that's, you know, not that interesting. It's got to be more than that. And I think people understand that in industry. I'm not picking on it, but these internships should be targeted and well formatted in a way that it's advancing the learning of the student. I think that's quite important. And, you know, the students need time. Students need time at the universities to do their research, and that research needs to be well funded. And so that's both the governments, so not just US government, but whatever country it is, but in the US, it's the US government primarily, and industry. And if we want to have a robust pipeline of people who are educated and coming out, they need to come from groups that are actually doing relevant research that industry cares about. So this balance has to be drawn. You know, for example, you know, industry might want to hire somebody who knows everything about how to design or operate a qubit, and they have to balance that against, well, am I willing to give funding to a university that might be doing sort of cutting edge research, but it makes me a little uncomfortable because it might be getting close to what I consider to be valuable IP today, right? So, but on the other hand, if we don't do that, and I've trained somebody on, you know, 20 years ago physics for quantum computing, and then you hire that person, how useful is that, right? And then now you have to train that person, right?
Makes sense.
So I don't really have an answer to all of that. I'm not sure that there is an answer, but this is a description of the issues that we need to work through. And, you know, I should say that we have working relationships with many companies, and it goes very, very well. So I think, you know, it's also a moving bar, right? That what is the right answer or positioning today is probably not going to be the same in 5 years or 10 years.
Those are very valuable insights and directions, Will. Thank you.
Sure.
So before I jump into the questions of the audience, and I see they keep populating on the YouTube channel, you know, let me ask you, you know, some forward-looking perspectives from you. So one of the questions, and you know, to this heart of the industry in particular, is looking at the integration with, let's say, HPC and AI. So how do you separate the hype from the reality in the near term? And from a hardware perspective, what are the most practical challenges to, you know, synchronizing these different computing paradigms and how it would come up together?
Yeah, I mean, that's a fantastic question. Don't have an exact answer. It's clear that quantum computers will need to run in tandem with high performance computers, right? If for no other reason that I value my fingers, I don't want them at 20 millikelvin, I need to actually program my algorithm on a classical computer, which then controls and sends signals down to, you know. So clearly that quantum computers will always be connected with conventional computers to operate, at least in this foreseeable future. But more importantly is, you know, to do quantum error correction, right? Which as we said, it's very likely going to be needed to realize the promise of quantum computing. To do that, we have syndrome measurements that are coming out every clock cycle of the quantum computer, and we need to do some type of analysis, maximum likelihood analysis, or something akin to that, to understand where an error, if an error occurred, where it occurred, and the type of error that it is, right? And then we need to decide, do I need to correct that right now, or can I wait a little bit and correct it later? And that depends on what gates are being applied to run the algorithm. Some gates we don't care, other ones, well, yeah, we got to correct before we do that gate. So all that has to happen. And so all of that decision making is done on a classical computer. And for platforms like superconducting qubits, which are quite fast, the HPC needs to be pretty powerful and fast itself, right? So this is all needing to happen. We're starting to look at that in our group here, and I know others are doing it as well. We're starting to work with NVIDIA and GPUs from NVIDIA. And that's going to happen more and more over time. Yeah. So I think that, at some point, we'll see quantum computers. I guess it's already happening. I shouldn't say at some point. That point is now. Small scale quantum computers of 50, 100, couple hundred qubits being sited in or next to a large, maybe top 500, but certainly large HPC, large classical computer. And people are just learning about how to network these together, right? And whether it's superconducting or neutral atoms or trapped ions, they all need to do it. So it's starting to happen, but it's going to unfold over time, and we have a lot to learn.
Fantastic. Thank you. Well, before we wrap up, I would like to take a few questions from the people watching on YouTube. So I've seen the chat populating, so I'm going to have to pick just a few of those. And there is one question I particularly like, which is, if William were to start his PhD today, what topic would he want to cover in the next 4 years? And if I may even expand further the question, what advice would you give to a new student that is looking into quantum? Is that too late? Is that the right time? Where should he or she or they be looking at?
Yeah, well, I do get asked this question sometimes, and I'll give the answer that I give, which is that what's important is that you do what you're passionate about and what you enjoy doing. And if I take a step back for a moment, we just talked a little while ago, right? We said, look, if quantum computing is going to become an industry, we're going to need people from across the university doing it, whether it's Sloan School of Management, chemistry, biology, physics, EE, whatever. So do what you enjoy most and find an advisor or a group that you can join that has a quantum connection, right? I'm hearing my parents in the background as I say this, but it's also smart because you've learned both a traditional discipline, in case it all falls apart, okay, you got something to fall back on, but at the same time, I think it's quite valuable because you become a quantum computing aware person who knows your field, at the level of an undergrad, master's, PhD, postdoc, whatever it is, whatever your terminal degree is. That's very valuable. And maybe you're a person who loves physics. We'll do that then, of course. But whatever you do, do that which you are passionate about, and then add to that quantum awareness or an application to quantum, or get engaged in quantum. And then I think you'll find that the skill set you have is quite valuable to industry, whatever that skill set is. And I say that because I know that companies like IBM and Google and AWS and Microsoft and Intel and others, if you can go online and look, who are they looking for, right? And there's a few of them that are, quantum physicists, but a much larger number are everything else, right? So I would say do what you're happy about doing, particularly as a PhD student, because it's a long haul, it's a delayed gratification, and there will be dark days. I had them, probably you had them too, Danny.
Oh yes, I did.
Yeah, and when it's dark, you can
also happy moments, I should say. Very happy moments as well.
More happy moments than dark days, but some days are dark, and you just have to say, okay, get a coffee and say, yeah, but I know that I really love this. So
what I hear is passion and motivation are going to be the key into this long marathon rather than sprint.
That's right.
So Will, maybe let me finish with one more question that seems to be intriguing several people in our audience today. What do you think is actually the current bottleneck for realizing an economically viable quantum computer?
Well, certainly two things. One is we need larger, more performant hardware. We need more qubits, and they've got to last longer than they do. Now, maybe not intrinsically, maybe with error correction, but That's number one. And I would say number two is we need more quantum algorithms. And by that I mean, like we talked about before, um, we need people thinking about not just, the big thoughts that we have at a university of like, here's this generic algorithm, right, that can solve, AX equals B. But we need somebody who's got a real problem in industry who's saying, okay, I'm going to take that idea and I'm going to apply it to my problem, and I'm going to, dot the I's and cross the T's and actually write down the whole algorithm and account for all the realistic things I need and understand how the classical computer is going to work in tandem with the quantum computer, all of that. And then at the end of the day, decide, how big a quantum computer do I need? How performant does it need to be? And what is the actual advantage I'm going to derive? Not the theoretical asymptotic advantage, but to the best I can estimate, what is the real advantage I'm going to get, right? And that's what we need to do if we're going to realize quantum economic advantage.
Fantastic. Well, let me be mindful of your time and everyone's time in the audience. So let me close it up here and say thank you very, very much, Will, for sharing your time and all these insights with us today.
Yeah.
As a small token of appreciation, we've sent your way the very first mug from our Qblox collection with our motto that says "Building Quantum Together." I don't know if you've received it yet.
It's right over there. I don't know if you can see it. It's the white.
I can see it, but I don't know if on YouTube maybe they have a wider screen. They can see it. Maybe you want to show it to the audience, Will, actually.
It's a coffee cup. I got a coffee cup. Yay.
Thank you for sharing that.
Yeah. No, thank you very much, Danny. I really enjoyed it. Of course, I always enjoy talking with you, and I hope that it was helpful and useful, and that most of what I said was actually true.
It was fantastic, Will, as always. So let me just finish by a word for those of you that have joined late, or maybe want to revisit part of the conversation. The recording will be posted on our YouTube channel, the Qblox YouTube channel. So please subscribe for this and future content. And of course, stay tuned for future talks in the webinar series. We have some very exciting speakers also lined up here. Thanks again for everyone joining us today, and thank you, Will, for being here.
Yep, thank you, Danny. Thanks again.